Okay, my friends, in this video, we're going to take a look at this idea of electronegativity, okay? So electronegativity is a word that we use when we're describing this interaction between two atoms as they come and they collide with each other. Now, when there's a collision between two atoms, there's a potential of an electron transfer, which means one atom might give up an electron to the other atom. Or, from the other point of view, one atom might actually take an electron from one of the other atoms. This is very common in the chemistry world. In fact, all ionic bonding is created this way. Okay, so because of this, it's really useful for us to predict which of these two atoms, when they do collide with each other, is going to be the one that takes the electron, and which one's going to be the one that gives it away. Okay, that prediction or that ability to gain an electron is called electronegativity. Okay, so things with high electronegativity are very good at gaining electrons. Things with low electronegativity do not gain electrons very well, which means they're more likely to give them away. Okay. Now, electronegativity is not like ionization energy, where it's actually related back to joules. It's actually a 0 to 4 scale that's been arbitrarily published or put together. And the way they did it is they found the element on the periodic table that's the best at doing it, which is fluorine, by the way. And they said, we're going to give fluorine a 4. And then they found the element on the periodic table that's the worst at doing it, and they gave that a 0. And then they ranked them all in between there, okay? So basically it's a 0 to 4 ranking, where do you sit, okay? This is one of those few cases we do not have a label, okay, as we go through this, right? Now, to be able to gain an electron, we need to have an ability here, okay? So if you think about it, if you're going to strip an electron from another atom, you need to have some sort of attraction to it. Okay, so that attractive force comes from our nucleus. We call that the electrostatic force. Okay, basically it's the positive charge from those protons in the nucleus. They are able to attract electrons and hold on to them. Okay, now every atom has a nucleus, and every atom has a certain amount of attraction for its electrons to hold on to them. But when two collide, it's possible that one of the atoms is actually stronger than the other one's nucleus. So that nucleus then, or that electrostatic force is stronger, it can strip electrons away from the other atom, okay? Now, how do you know which one's gonna win, right, between those two things? So the biggest idea is which of the two has a stronger pull from the nucleus. And it's not about the number of protons inside the nucleus, because the number of protons is already always canceled out by the number of electrons that's also there. So there's always a balance between protons and electrons. So to take an extra electron, that nucleus has to have something unique to it in comparison to the other atom, okay? And really, it all comes down to size again, okay? So if you recall, the closer a nucleus is to its outer edge, the stronger its attraction is, okay? Okay, so what that means is the absolute smallest atoms, okay, the smallest atoms that we have, or the smallest element that we have, would be the best at gaining electrons, okay? I already mentioned that fluorine is the one that is the 4. It's the highest in electronegativity. Well, fluorine, if you look at it, it's in the upper right-hand corner of our periodic table, which is one of the smallest ones out there, okay? The atoms that are very big are horrible at this. They're not good at it because their nucleus is so far inside their atom, and they're so big that their nucleus can't really attract it, okay? So knowing this, what we should be thinking is that the smaller the atom, the higher the electronegativity. The bigger the atom, the lower the electronegativity, okay? So let's go to the iPad here, and we'll kind of show what I mean by that. So what I've done here is I've drawn a cesium atom right here, and I've drawn a fluorine atom right here, okay? And we're kind of relatively looking at the idea of their sizes, okay? So if the fluorine atom were to come in contact with the cesium. So let's say the fluorine atom's flying around doing its thing, and they collide with each other, okay? In that collision, now if we actually take a look, cesium's nucleus is way inside of here. So from here all the way out to here, this distance is really far. It's really far away. So any electrons hanging out here are not really held very well by cesium. In fact, cesium only has 1 electron out there anyway, so we'll just put 1 electron out here, okay? For fluorine, if you take a look, its nucleus is also in the center, but its nucleus, once it collides, actually is really close to that electron, okay? So that outer energy level of cesium is much closer to fluorine's nucleus and much further away from cesium's nucleus. So because fluorine is closer in that collision, when they separate from each other, get all this junk out of the way here. Okay, so let's say we have that one electron here. Okay, when they separate from each other, fluorine will steal that electron away. Okay, so it was on cesium, fluorine will steal that away. Now, what does change some things, right? So as a result, fluorine's going to hang out pretty close to cesium because it now has an extra electron. The fluorine will now have a negative charge on it. The cesium will now have a positive charge on it because there's an electron transfer. And as a result, we do get what's considered that ionic bond between these two things, okay? So the reason why fluorine's better at it, because it's smaller, okay? Let's go to a graph and see if our prediction makes sense. So we take a look here, and sure enough, here's our electronegativity scale from 0 to 4. And here's the atomic numbers. We see that we have lithium right here. We have sodium, potassium, rubidium, cesium, yttrium down here. And we notice that fluorine, chlorine, bromine, iodine, astatine, all of our halogens, or our group 17 elements, have the highest electronegativities in their respective periods. So when we go from lithium to fluorine, which is going across the second period, lithium is the biggest element, fluorine is the smallest. We go over here, rubidium is the biggest in period 5. Iodine is the smallest in period 5, okay? So that matches for sure our trend, where the smallest element in every period is the best at doing it. Now notice also, if we compare fluorine to chlorine to bromine to iodine, we're not actually drawing that line, but if we actually connect the dots this way and drew a line across this, we would see that fluorine, again, is smaller than chlorine because it's the smallest one in the 17 group, or that column. Fluorine is better than bromine, bromine is better than iodine, iodine is better than astatine as we go down those groups, okay? So again, the trends we see match perfectly what we were talking about in there. Now, what about these discrepancies though? Okay, so we know the trend works. Okay, so if you're filling this out on your periodic table, as you move to the right across the periodic table, your electronegativity is going to increase. As you move up the periodic table, your electronegativity is going to increase. Okay, so what about some discrepancies? Well, we got zinc right here, we have cadmium right here, we have mercury right here, we have yttrium right here, which they're somewhere in the middle here, and all of a sudden they dip, and they dip, and they dip. So we see these kind of weird dips. We even see the dip kind of here also, okay? Notice these are color-coded, main group, main block, transition metals, and so forth. So it looks like at the end, or the last element in that D block, we all of a sudden get this dip in electronegativity, okay? So let's talk about why that might happen, okay? Also, is there something missing from this, okay? Is there some sort of elements here that we're not seeing, okay? Think about that for a second, and then we'll move on. Okay, here's our reasons why. It comes back to stability again, okay? So once again, the trend of why electronegativity changes to the trend is based off of size, okay? The smaller you are, the more electronegative you are. The smaller you are, the better you are at gaining electrons, okay? It's good to note here that this is not about the fact that fluorine has 7 valence electrons, and if it gets one more, that it can have its magic number of 8, okay? There's a kind of a misconception, excuse me, that as you move from left to right across the periodic table, the reason why fluorine and chlorine and bromine, like those halogens or oxygen or sulfur, are negative ions is because they want their electrons more. So because they have 7 valence electrons to start, that they will have, because they only need one more, they just want to have that one more than somebody else. That's not actually true. It's actually a way I was taught when I was in like high school science. I remember my teacher saying that the reason why they gain electrons is because they want it more. And I'm like, okay, but that's not true at all, okay? So it's not about wanting things. It's not about, oh, they know that they're more than halfway to 8, so they're going to decide to get them versus give them away. It's 100% size. It's all about size, okay? It's true that the smaller atoms also have more electrons there, so there is a correlation there, but not a causation, okay? So yeah, the smaller atoms are just better at getting electrons. That's all it comes down to. It's not about the ratio between, how far they are to that magic number of 8 at all, okay? So our trend is based off of size. So then the discrepancies, like before, are based off of stability, okay? So let's kind of go through a few ideas over here. Why are the noble gases excluded? Hopefully you noticed or maybe were wondering, wait a minute, why do we stop at fluorine? Why are we not mentioning helium or argon or neon? Like, why are the noble gases not on here, okay? There's actually a break in the graph right here where helium should be. Well, think about this. Electronegativity is all about the ability to gain electrons when you are bonding. Noble gases don't really form bonds, okay? Noble gases are already stable. So they don't really take part in ionic bonding or covalent bonding. They're usually separate. They're all on their own, okay? So because noble gases don't really bond, they don't really participate in chemical bonding, we exclude them, okay? Now, that doesn't mean if you look them up, they're not going to have a number there, because they do have a number. But for our purposes, we're going to exclude them. So we're going to say the noble gases, because they don't bond, are excluded from this conversation, okay? Now, we see this dip at zinc, cadmium, and mercury, right? Zinc, cadmium, mercury, okay? And if we look, it's at the end of the d orbital for each time. Okay, so let's talk about it. Again, electronegativity is the ability to gain electrons, okay? So zinc has a full d orbital. With a full d orbital, okay, its ability or its need to gain electrons is much less than the elements around it, because that full d orbital creates stability. So the more stable you are, independent of your size, means that you will have a smaller electronegativity, okay? So even though zinc is relatively the same size as the things around it, we see a dip with that, okay? So we see that dip fall here. So again, we see that happen. Now, we notice that, yeah, zinc is stable, cadmium more stable, mercury more stable. Even the yttrium back here, that's more stable because we're ending the f orbital here, okay? So this is for the same reason, okay? But one thing we might notice is that it doesn't bounce back right away. So the element right to the right of it doesn't bounce back. It takes a couple elements before it regains that trend, okay? It's almost like a resetting of the trend at this point, okay? Well, think about it. Once we go from being stable at zinc and move one electron to the right, where we be gallium, now gallium is the biggest element, and it has one electron in that p orbital, okay? So now gallium is a fairly unstable configuration, and in comparison to the things around it, it's the biggest one, okay? So it's almost like we're resetting the scale after we go through the D block, and then it kind of resets itself. It has to build itself back up. So again, being big in comparison to the rest of the p block and being relatively unstable means that this is going to have the least ability to gain electrons. And then as it moves up to finish out to bromine, that ability to gain electrons is going to increase and increase and increase and increase again, okay? So we see that happening in all cases where it drops down and then it takes a few to get back to where it was, okay? Even here, this little dip here, this little dip here, those are half full orbitals, okay? So this is the halfway point for the d orbital. So we even see that a little bit at the half full point, okay? Now, you're responsible for what's going on here at the zinc, cadmium, mercury, at that 12 to 13 kind of border, like we said before. So you're responsible to be able to describe why we see this discrepancy in this electronegativity trend and why the noble gases are excluded, okay? Now, last question. Does this trend align with the ionization energy, okay? Or how is it different? Well, if we go back to ionization energy, go back a bunch of slides. okay, we saw lowest ionization energy at the alkali metals, the big atoms, and we saw high ionization energy at the end of that period, okay? So if you look at it, the trends actually do align. They align with each other very, very well, actually, okay? So the general trend is the same. There is correlation there. So think about it. If you are a small atom and you're really good at gaining electrons, okay, that means when you get collisions, you're going to be stripping those electrons away. So if you're really good at gaining electrons, wouldn't it also make sense that it would take a lot of energy to take them from you? Okay. So the analogy I often use is think about like a friend of yours that you may know. I have a friend in college, wonderful person. He was one of the most frugal people, cheap people that I knew. Okay. He was making money all the time. He was working hard. He was constantly gaining money and saving it and saving it and saving it. Okay. But for me to get him to go out and spend any money, like, hey, let's go to the movies tonight. It's like, nah, it's too much money to spend on a movie. It took me so much energy to get him to go out and do anything fun because he had such a tendency to want to gain money and hold on to money that it really took a lot of work to get him to spend any. It's the same thing for atoms, okay? If you're really, really, really tiny, you're great at grabbing electrons, which means it's super hard to pull them away from you. So those actual trends actually align with each other very, very well. Now, how is it different? There are some significant differences, and that comes to where the discrepancies are, okay? So if you remember, for ionization energy, when we got to zinc, cadmium, and mercury, we saw this thing spike upwards, okay, not drop down, because they were stable. So in terms of stability, the more stable you were, the harder it was to take electrons away from you. Well, the exact opposite is true for electronegativity. So the more stable you are, the less likely you are to gain them, okay? So that's where the differences come into play, is how the discrepancies responded, okay? Same reason, because it's still about stability, but for ionization energy, we saw an increase, an abnormal increase. For electronegativity, we see that dip or that decrease, okay? And the other thing that makes them different, obviously, is that we're excluding noble gases for the electronegativity here, where we didn't exclude them for the ionization energies, okay?